Hey guys, so this is the fourth video I guess on multivariable optimization, and in this video I'm going to discuss question 3 now. In the previous parts we discussed question 2, and I hope I've discussed all of the parts. Let me just check if I've missed some part of question 2 or not. Mm. So yeah, so we have discussed all of the questions from question 2, and now I'm going to start with so now I'm going to start with question 3. So in the previous video we discussed question 2 part D, and now we are going to solve question 3. Question 3 of exercise 17.3. Exercise 17.3, Sydsaeter and Hammond. Multivariable optimization. Also, if you are watching this video for the first time, I would suggest you to watch the first video of multivariable optimization, where I have discussed extreme value theorem and what we are exactly doing here, right? And then you can watch my subsequent videos, right? So yeah, let's just start. So the question 3 says that let the domain of the function h be the set of all x comma y satisfying both x lying between 1 and 2, y lying between 0 and x minus 1. Let hx comma y is equal to x square y into x minus y minus 1. Prove that h has global extreme points and find them. Right. So the question says that, let me just write the whole question. Question says that h be the set of all x comma y satisfying both x lying between 1 and 2 and y lying between 0 and x minus 1. Let h x comma y equals x square y x minus y minus 1. Prove that h has global extreme points. Prove that h has global extreme points. Right. Prove that h has global extreme points. Right, so let's just start now. Firstly, we'll find the stationary points of the function h. So hx comma y is equal to x square y x minus y minus 1, and I can write this as x cube y x cube. Let me just erase this. So I can write this as x cube y minus x square y square minus x square y, right? Minus x square y. Now finding the partial derivatives of h with respect to x. So del h by del x will give me 3x square y minus 2xy square minus 2xy. Del h by del y, which is the partial derivative of the function h with respect to y, will give me x cube minus x square 2y minus x square equals to 0. So 3x square y minus 2 xy whole square minus 2xy. X cube minus 2x square y minus x square. Now we'll find the stationary points by solving these equations, right? So what I can do is I can take y common from the first equation, and I can take x common from the second equation. So taking y common will give me, I can take xy common actually, xy common. So this will give me 3x minus 2y minus 2. which is equal to 0, and taking x common from here will give me, or taking x square common from here will give me x minus 2y minus 1. X minus 2y minus 1. Just give me a minute. I would just bring my charger for my Apple Pencil. Just give me a minute. So after taking x square common, I will be left with x minus 2y minus 1, right? So now what I can do is I'll just solve these two equations. Now from this equation I can say that from this equation, from equation 3 and equation 4, right? So from equation 3 I can say that x is equal to 0, or we can say that y is equal to 0, or we can also say that 3x minus 2y minus 2 is equal to 0, right? But can x and y be equal to 0? Let's just see. First of all, when we are writing the function, when I was writing the question, there was a statement given in the question which says that let h be the set of all x comma y satisfying both x lying between 1 and 2 and y lying between 0 and x minus 1, right? What this means is that x lies between 1 and 2. That means that x cannot be less than 1, right? And y cannot be less than 0. But here I am saying that x is equal to 0. So basically we will reject this. This is not possible. This is not possible. This is possible. This is possible. Why? Because y is lying between 0 and x minus 1. Now coming back to this equation. This will be my fifth equation. Now from equation 4, I can say that x is equal to 0 because x square is there. So x square is equal to 0 implies x is equal to 0, but I'll reject this, not possible. Then moving on to x minus 2y minus 1 equal to 0. This will be my equation 6th. Now solving equation 5 and 6, right? So these are my 5 and 6 equations. Let me just draw a circle over them. Duplicate. Let's just take them below. Right. So I'll just now I'll just solve these equations. So solving them, x minus 2y minus 1. So this becomes 3x minus 2y equals to 2, x minus 2y equals to 1, and I'll multiply this second equation by 3. So this will give me 3x minus 2y is equal to 2, 3x minus 6y is equal to 3, subtracting this, adding this, and subtracting this. So this will get cancelled. This will give me 4y equals to minus 1, y is equal to minus 1 by 4. Let me just check. I think I've made some kind of mistake. X minus 2y is equal to 1 and 3x minus 2y is equal to 2. So if I just multiply this equation by 3, 3x minus, wait a minute, I could have just cancelled 2y here, right? So I didn't need to multiply this equation by 3. I could have just cancelled 2y. So I made this blunder. But let's just see, still we should be getting the right answer then in that case also. So minus 1 is positive. Y is equal to minus 4, minus 1 by 4. But this cannot be possible. Why? Why cannot this be possible? Why can this be not possible? Because y lies between 0 and x minus 1. Because y lies between 0 and x minus 1, we will reject this point. Right? We will reject this. Reject. As y lies between 0 and x minus 1. So basically we don't need to find x now because the whole point won't be feasible, right? So the point that we have finally is y can be 0, y can be 0, only this y is equal to 0 is what we have right now. We don't have the value of x. Let me check my calculation once. So if I take xy common, 3y, 3x minus 2y minus 2 minus 2. So if I take x square common, x minus 2y minus 1, x minus 2y is equal to 1, which becomes 3. 3x minus 2y equals 2. Solving these equations gives me minus positive, cut 1 1, 2x is equal to 1, x is equal to half again. Even if I find the value of x here, after putting in y is equal to minus 1 by 4, what I'll be getting is x minus 2 into minus 1 by 4, which is equal to 1, which was equal to 1, right? So x minus 2 by this equation. So this will give me x is equal to half. But then we also know that x lies between 1 and 2. 1 and 2, it was given, right? 1 and 2. 1 and 2, right? So we'll reject this again, right? So now let's just move on. So this is the only point which we have got right now, and we don't know the value of x. So we can say that y is equal to 0 and x lies between 1 and 2 can be one of our points, right? But y should be 0. Or wait a minute. We were also given that in the question that y lies between 0 and x minus 1. Y lies between 0 and x minus 1. So we are saying that y lies between 0 and x minus 1. So if I just put in the value of 0 in place of y, I'll be getting x minus 1. So x is greater than 1, right? If I just move 1 to the left hand side of the inequality, I'll be getting x is greater than 1. And we are also given, and we are already given that x lies between 1 and 2, right? So we can say that y is equal to 0 and my x lying between 1 and 2 is one of my points of concern, right? Is one of my points of concern. Now if I just try to use the constraints or to find the boundary points or the points on the edges, I'll be using this equation and this equation. So if I just draw so let's just draw a line here and just ignore this for the moment, right? Let me just draw a line and ignore this for a moment. So we are given x lies between 1 and 2, y lies between so when my x is equal to 1, my y will be between 0 and 1, and when my x is equal to 2, my y will be when my x is equal to 1, my y will be this. So basically y equals to 0. When x is equal to 2, my y will lie between 0 and 1, right? So basically I can say that my y will always lie between 0 and 1, right? Now if I just draw a graph, right? Now I'll draw a line y is equal to x minus 1. I'll just draw a line which is y is equal to x minus 1. Y is equal to x minus 1. y is equal to x minus 1 means when y is 0, x is equal to 1. So when y is 0, x is equal to 1. This line will start from here. This is the y axis, this is the x axis, and now I'll just draw this graph. This line will start from x is equal to 1. This line will be somewhat like this, and the slope is positive. The slope is positive, right? So this will be an upward sloping line. This will be an upward sloping line, like this. Like this will be a straight line. So this will be a straight line, and this line is y is equal to x minus 1. When y is 0, x is equal to 1. And now we were given the inequality that y is less than equal to x minus 1. So this area is basically y greater than this area is y greater than x minus 1, and this area is y less than x minus 1. And we were given y is less than equal to x minus 1. So basically all the points lying on this line, along with all the points in this area, right? So we can include all of these points and all the points lying on this line. So now let me just erase this part, right, and let me just shade it using a black pen or somewhat like this area, and all the points lying on this line, right, and all the points lying on this line, basically on this line, this whole line. Now let me just remove this. And now we are also given that x lies between 1 and 2. X lies between 1 and 2. So when x is equal to 2, my y will come out to be, when my x is equal to 2, my y will come out to be, I have already shown you, y will be, if I just draw a line here, if I just draw a line from x is equal to 2, this point, this is the equality point. When y will be 2 here, if I just insert 2 here, 2 minus 1 will give me 1. 2 minus 1 is 1. So basically I'll be getting 1. So y is 1 here. Right? So y is 1 here. So now I have this point. This point is 2 comma 1. This point is 2 comma 1, right? I hope my 2 is clear to you. 2 comma 1, and this point is 1 comma 0, and this point is 2 comma 0, right? Now let me just zoom out a bit, right? So these are my first, second, third, 3 edges, right? 3 edges. So if I just take the first edge, edge 1 is basically when my x lies between 1 and 2 and my y is equal to 0, right? Now I just write the function again. The function given to us was this. Let's create a duplicate here. This was the function given to us, right? If I just zoom it a bit, I hope you guys can see. So at edge 1, x lies between 1 and 2 and y is 0. So if I just put in y 0 and x, so this will give me x into 0, x square into 0. So this whole term will become 0, and if I just write this will become x minus 1. Wait a minute. Oh, I'm sorry, I had just written this. So yeah, so this will become 0. This is an equality sign, right? So I just opened the terms and shown you just so that the calculation becomes easier, right? So this is an equality sign. So if I just put in 0 here, also if I just put in 0 here, also if I just put in y equals to 0, this will become 0, right? So basically the function becomes 0 when my x is lying between 1 and 2 and my y is equal to 0. So I have another point, hx comma 0 is equal to 0, y is equal to 0, and x lies between 1 and 2. Now at h2 I have all points where my y is x minus 1, where my y is equal to x minus 1, and my x lies between 1 and 2, right? So if I just put in x comma x minus 1, right, I'll be putting x minus 1 in place of y. This was the h2, right? Wait, sorry, this is the h3, this line, right? So this line I'm solving first, h3. So this is the h3, so if I just substitute value of x minus 1 here in place of y, so x square into x minus 1 into x minus 1 minus 1. So basically this also becomes 0. hx comma x minus 1 will give me x square into x minus 1 into x minus x plus 1 minus 1. So this will be cut, and this also becomes 0 because this whole term will become 0, right? So hx comma x minus 1, so hx comma x minus 1 is equal to 0 when x is lying between 1 and 2, x is lying between 1 and 2, right? And y is equal to x minus 1 again. Now h2 says that x is equal to 2 and my y equals to, my x is equal to 2 and my y lies between 0 and 1. If I just show you guys, right? So this line on all points on this edge, I have x is equal to 2 and y lying between 0 and 1. So if I just move on and substitute the value of 2 comma y, I'll just substitute x is equal to 2, or let me just write this a bit more clearly. H is equal to x equals to 2 and y. If I just substitute x is equal to 2 comma y in this function, I'll be getting wait a minute, where's the function? Yeah, this was my function. I'll just copy this function, just copy this part, duplicate, So if I just substitute 2, so sorry, so if I just substitute x is equal to 2 here and y, this will give me 4y, and 2 minus 1 is 1 minus y, right? And now this has become a single variable function. The only variable present now is y. So I can write this function as, I can write this hx equals to 2 comma y as a function g of y, and this will give me 4y minus 4y square. Now I'll be finding the first derivative of g of y to understand the nature of the function g of y, right? Where is the function increasing, where is the function decreasing, how is it moving, right? So 4y minus 8y, this will give me a stationary point, which is y is equal to half, right? This will be my stationary point, one of my stationary points, right? So y is equal to half. Now I can check the nature of the function by checking the value of the derivative, how the derivative is moving around half, y is equal to half. So if I just substitute any value, of y greater than half, I'll be getting the value of the derivative as first derivative as negative, right, and positive. So if I just substitute 4 minus 8y, if I just substitute y is equal to 0, which is less than y, which is less than half, I'll be getting 4 minus 0 equals to 4, which is greater. So my g dash y is positive on all points to the left of half. On all points to the right of half, if I put in any value, for example y is equal to 1, I'll be getting 4 minus 8, which is negative of 4, which is less than 0. So basically my g dash y has become less than 0 for all y greater than half, and here g dash y is positive for all y less than half, right? So there was no need to show you guys all of this, but yeah, let me not erase it. I'm just keeping this up so that when I upload the PDF you can take a look. But this is the part of the single variable optimization, chapter 8 or 9 from this same book, Sydsaeter and Hammond. I might discuss this chapter also in the upcoming videos, right? But if you are watching a video on multivariable optimization, I hope you must have seen or read or studied single variable optimization, right? So now I know the nature of y. So I can say that my y is equal to half is a local maxima, right? Because I am getting a dome-like structure. So I have explained these concepts in the previous video also. So I am getting a dome-like structure where my y is equal to half. So this is turning out to be a maxima. Local maxima. I'm saying a local maxima. Actually, it is a global maxima also, because I'm not given any constraints here. But I'm just writing local maxima for the time being. And look, global implies local. So y is equal to half. Now let's just check our function at y is equal to half. So I have a point g of half, which is also equal to h of x equals to and y equals to half. So now if I just substitute the value in this function only, I'll be substituting the values, right? So g of half will give me 4 into half minus 4 into 1 by 4. So 4 into half minus 4 into 1 by 4. So this will give me 2 minus 1, which is 1. So my h of 2 comma half gives me 1. Now if I just find the value of h at h of 2 comma 0, right, and 2 comma 1, because my y is lying between 0 and 1, because my y was lying between 0 and 1, so I'll be finding these values also. These are basically the corner points, and we should find the value of the function at these points also. So h of 2 comma 0 will give me 2 comma 0. 2 comma 0 will basically give me 0, and h of 2 comma 1 will basically give me 4 into 1 minus 4 into 1, which is also equal to 0. 4 into 1 minus 4, yeah. So this is also equal to 0. I guess I've moved to the end of the page, right? So now what I have is this. This is the one of the most important things that we have found here, right? This is also equal to 0, and h of 2 comma 1 is also equal to 0. Now we can, I guess, find a conclusion for all of this. So the points that we found using the edges were, we are getting 0 at all these points, we are getting 0 here also, right? And before this we also found that so if I just substitute x comma 0 at all points, I'll be getting 0 only. I have found this on edge 1, right? So H1 was all about, H1 was all about, H1 was all about x lying between 1 and 2 and y equals to 0. So I'll be getting the functional value as 0. Now we can just write our global maxima and minima points. So basically I have my global maxima at x is equal to 2, y is equal to half, which is equal to h of 2 comma half equals to 1, which was 1, right? Here it was 1, right? So here was 1, right? Yeah. So 2 comma half is 1. Right? And my global minima will be, so 0 here also, 0 here also, h1 and 3 are also giving me zeros. So I'm getting 0 on all other points. On all other points except this point. So global minima h of x comma x minus 1, which is equal to 0 at all x lying between 1 and 2 and y equals to x minus 1. Now this will also be a global minima where my y equals 0. Obviously I've covered all of the points from this statement, right? So whenever my x will be 1, my y will become 0. Whenever my x is 2, my y will become 1, and it will give me a value of 0, right? So if I can just see here, right, my x is lying between 1 and 2. This already accommodates this point, right, where my y is becoming 0, right? When my x is equal to 1 here if my x is equal to 1, my y will become 0. So automatically this point is covered, right? Because here in this statement x is lying between 1 and 2. So if I just substitute the value of 1 comma 0, I'll be getting a value of 0. And this statement is saying that y is equal to x minus 1. So whenever my x is equal to 1, my y will automatically become to 0. So both of these statements are saying almost the same thing. And this was also saying the same thing. When my y is equal to 0 and x lying between 1 and 2, I'll be getting a value of 0. hx comma y is equal hx comma 0 is equal to 0. Right? This was also saying the same thing. Right, at x, and here what we had is, here we had x is equal to 2 and y lying between 0 and 1. I'm not writing this because at exactly y is equal to half, we were getting a value of h2 comma half is being equal to 1. So we have our global maxima and global minima points. Let me just check my answer once, right? I hope you guys got what I did, right? Let's just check our answer once. This was a pretty short question, not too long. Just give me a minute. I'm opening the PDF and I'll share the PDF with you guys, right? So I guess I can open the PDF now. I hope you guys see. I hope you guys can see. So let me show you guys the answer. Oh, I don't have the question third's answer, right? So this is only the even question's answer. The answer to the third question is at the back of the book. Wait, let me just check. So basically, they give the answers to the odd questions at the back of the book, and for the answers to the even question, I had to download a PDF. That's why I was sharing the PDF with you guys. Earlier we were doing question 2, so that's why I was opening the PDF and showing you guys. I don't have the answers to the question 3 in this PDF, but it's written at the back of my book. Let me just check. Right, so the maxima exists at 2 comma half. The minimum is 0 at x is equal to 0, x comma 0 and x comma x minus 1 with x arbitrary in 1 comma 2. Right? Yes. Basically, exactly what we wrote. They have written this also, that x comma 0 is equal to 0. This is also part of global minima, where my x is lying between 1 and 2. But basically this statement is already implying this statement. Why? I explained you guys. Oh, wait a minute, my screen is not sharing. So basically so basically they have written this statement also, right? But what I'm saying is that this above statement which I wrote earlier, right, this is also implying the same thing. This is also implying this also. Why? I explained you guys, when my y is x minus 1 and my x becomes 1 equal to 1, when my x becomes equal to 1, this will automatically become 1 minus 1 equal to 0, right? So basically this statement is this whole statement, this statement is already implying this statement, right? There was no need actually to write this, so I'll be just removing this, and other than that our answer is absolutely correct, right? So I hope you guys enjoyed the video. If you enjoyed the video, please subscribe to the channel and share the video with your friends if someone is interested in solving some questions on multivariable optimization, right? I'll also be sharing the PDF with you guys in the description. So yeah, just keep watching the videos, put in a like, put in a comment, that encourages me to put in more videos, right? So thank you, and I hope to see you in the next video. Bye bye.